Gradient boosting, it's one of the most powerful tools we have, right? But it's got a dark side. It has this tendency to overfit. If you're not careful, it'll build a model that looks absolutely perfect on your training data and then completely falls apart in the real world. Today, we're going to learn how to tame that beast. Welcome to AI and Machine Learning Deep Dives. In this explainer, I'm going to show you exactly how to build robust, generalizable gradient boosting models. You know, the kind that perform brilliantly on data they have never, ever seen before. So let's set the scene. You've just trained a model. It looks incredible. The scores are great on your training set, but when you test it, it's a mess. That is a classic and super frustrating sign of overfitting. If that sounds even a little bit familiar, stick around. I'm going to show you exactly what to do about it. Okay, take a look at this chart. This right here is the problem in action. Think of this as our patient on the operating table. Now, zero in on that orange line. That's a model with absolutely no breaks, no regularization. It starts off pretty well, right? The error goes down, things are looking good, and then it makes a hard turn. The error on the test set starts climbing and climbing and climbing. This is the moment it stops learning and starts memorizing. That's overfitting. And just so we're all speaking the same language here, let's break this down real quick. The bottom axis, boosting iterations, that's just us adding more and more little decision trees into the mix. And the vertical axis, test set deviance, well, that's the one that really matters. That's the model's error on brand new data it's never seen. When that number goes up, our model's actually getting dumber. So what's our first line of defense? What's the first tool we pull out of the bag? It's a fantastic technique called shrinkage, which is controlled by the learning rate. The whole idea here is to slow things down. Instead of letting each new tree make a huge, aggressive fix to the last tree's mistakes, we shrink its contribution. We force it to learn more cautiously. Here's a way to think about it. Without shrinkage, your model is basically taking these giant, reckless leaps to try and fix every little error it sees. It's overreacting. But with shrinkage, we're forcing it to take small, careful, deliberate steps. Each new tree only makes a tiny, softened correction. It's this cautious, conservative approach that helps it find the real pattern instead of just chasing the noise. And that leads us directly to our first big rule. This is takeaway number 1. Use a small learning rate. Honestly, it's probably the single most important knob you can turn to force your model to be more careful and to avoid overfitting. Now, slowing things down is great, but we can also get more direct. We can put some hard limits on the trees themselves. We can use things like max depth to stop them from getting too complicated and deep. Or we can use parameters like min child weight or min samples leaf to tell them, hey, don't you dare make a decision based on just a handful of data points. The logic here is just so simple and powerful, right? If your building blocks, the individual trees, are simple, the whole building is going to be stronger and more robust. So that brings us to takeaway number 2. Keep your individual decision trees simple by constraining their growth. All right, our third major strategy is a bit different. We're going to fight complexity with randomness. It's a technique called subsampling. The idea is brilliant. Instead of showing every single tree the exact same complete data set, we give each one a slightly different random piece of it to look at. And we can do this in 2 main ways. We can subsample the rows, which means each tree only gets trained on a random fraction of our data points, or, and this is also super effective, we can subsample the columns. This means each tree only gets to see a random handful of the features. It's kind of like getting a second opinion or preventing groupthink. You force each tree to learn from a different perspective, which makes the whole ensemble much, much smarter. This forced diversity is just an incredibly powerful way to slash the model's variance and stop it from overfitting. And that brings us to takeaway number 3. Introduce randomness by subsampling your data and your features for each tree. So, there we have it. Our toolkit is full, right? We have shrinkage, we have tree constraints, we have subsampling. The standard advice is just to use these things aggressively. But is that always the right move? What if I told you that sometimes the rules can change completely? And now for the big reveal. On the left, that's our original chart, remember, from a pretty small data set. The orange line with no shrinkage is a disaster. It overfits like crazy. But now, look at the chart on the right. This is the exact same experiment, but run on a much, much larger data set. And, whoa, that same orange line is now one of the best performers. With more data, the overfitting problem, it's practically gone. This shows us something absolutely profound about machine learning. Your best settings are not written in stone. They depend entirely on your context, and especially on how much data you have. The rules that work for a small data set can be completely wrong, even harmful, for a large one. You see, with enough data, the model can learn the true signal so well that it's no longer tempted by all the noise. The data itself becomes the best regularizer. And this brings us to our final and maybe the most important takeaway of all. Takeaway number 4, sometimes the best defense against overfitting isn't a clever new technique, it's simply more data. So, let's put this all together into a handy checklist. When you see that overfitting curve start to creep up, what do? 1. Start with shrinkage, a small learning rate. 2. Constrain your tree complexity. Keep them simple. 3. Inject some randomness with subsampling. And 4. Always remember that more data can change the entire game. Let's do a lightning-fast recap. Takeaway number 1. Use shrinkage to learn cautiously. Takeaway number 2. Keep your trees simple. Takeaway number 3. Subsample everything you can. And the big one, takeaway number 4, the size of your dataset is key. It changes everything. And that leaves us with a really fascinating question to chew on, doesn't it? We just saw a golden rule, always use shrinkage, get flipped on its head when we got more data. So what other best practices, what other rules of thumb that we all follow in machine learning, what else might need a second look as we move into this era of bigger and bigger data sets? That's all for now, folks. Please like, share, and subscribe for more like this.